Hello, everybody, and welcome to the final technical session of the day. So we have two speakers in this session on compressible flows 1. So the first speaker is Dr. Ehsan Mahravan, and he's going to talk to us about shock interface interactions for compressible fluids using the ghost fluid method. So Ehsan, you're welcome to turn your video on, and you're welcome to share your screen. So I can just remind everybody that you can ask questions in the Q&A session or in the discussion forum. And it is probably good to remind people you get points as well for interacting with the event as well, so you can increase your chances of winning a prize at the end. Great. Okay. Ehsan, feel free to share your screen now as well.
Thanks, Philip. Yeah. Let me.
Perfect. Okay.
So, there you go. Hello, everyone. I'm Ehsan Mahravan, and I am going to talk about shock interface interaction simulation using compressible gauss fluid method solver that we've developed in FOAM. So, when we have two different materials, there is always a jump at the interface because of the different properties, and this causes numerical instability, and we need to somehow treat this problem. One method is to fit the mesh, so it lets us to sharply simulate the problem, but it doesn't suit large deformations. And the most common approach is to define homogeneous properties using level sets, law of front tracking, or any other methods of this kind. So we kind of smearing the interface and lose the accuracy. And another approach is gauss fluid method, which lets us to deal with large deformations and complex shape changes and yet have a sharp simulation. In gauss fluid, we simply divide the domain to two parts, phase A and phase B. The location of the interface is tracked using level set or any other method that is available. Level set is the most common method. And let's assume that we are going to solve phase A. We solve each phase separately. So let's assume that we are going to solve phase A. At this time, phase A is called real fluid, and phase B is called gauss fluid, and its cells are called gauss cells. So when solving phase A, we need values from phase B, and we should populate the values on cells from phase B, and here is the difference between the methods in gauss fluid. Every gauss fluid method suggests a different way to populate gauss cells. So so far, gauss fluid method can be applied to any kind of interface discontinuity of any two material. What we have developed is compressible solver and compressible incompressible solver that I'm going to present the first one here. The original method simply extrapolates the discontinuous variable to the gauss region, and entropy and tangential velocities are discontinuous variable that we normally deal with in compressible inviscid flows. And we keep the continuous variable unchanged. So entropy is used instead of rho, because using density leads to so-called overheating problem, which is an overshoot in temperature. So the method name fails for the starting shock this is the original method and it fails for a sonic shock, then we need modifications. And all the modifying methods out there use a Riemann solver to resolve the interface condition. So we need the left and right state, which is QL and QR. They are interpolated away from the interface, and then we construct a Riemann solver across the interface, solving the Riemann problem. We have Q star L and Q star R, and using Q star L and Q star R, we can populate Gauss cells. And here again, there are some variants. The first modified Gauss fluid method was introduced by Liu and Hu. They solved characteristic equations to find Q stars, and they use the entropy that they found from solving Riemann solver for the interface and give it to two sides of the interface, left and right, and then the rest of the method is just like the original one, extrapolating constantly to the Gauss region and keeping continuous variables unchanged. And there's another method which uses exact Riemann, and after finding the SR state, it gives the left state to the node I, and then extrapolate the whole state to the right. And the last one is the OTM Pichet. It's just the same, but it uses an approximate Riemann solver like HLLC to resolve the interface. So in 2D, again, we divide the domain to real and Gauss regions, find the interfaces, construct the Riemann solver in direction normal to the interface. And after resolving the interface and finding QSR for all of the interface cells, we do the constant extrapolation using this relation that I provided here. So the solver that I have developed is named GFM CompFOAM. It's developed inside within FOAM extent, FOAM extent 4. And I use HLSC Riemann-based solver with fourth order Runge-Kutta time integration based on the originally existing DBNS form for each phase. And then for tracking the interface, I use level set. For the examples that I will present here, I use third order TBDRK and fifth order Venn algorithm. This discretization is only available for a structured grid. So to implement the solver, I needed to modify two libraries, term physical models and DBNS. Term physical models in FOAM extent can only handle one phase per solver. So I added name to this library so that it can have more than one phase. And STFN gets EOS, which is quite popular for simulation of wave propagation in water, is added. And some functions for that I needed for HLSC and Gauss fluid method are also added to the library. On the other side, DBNS, which is consisted of the solver and the library, it originally only handled idle gas EOS. I've changed it to work with general EOS, and all of the equations were hard-coded, so I linked them to term physical models library, and it was single phase. Now it works with multiple phases, and it was enthalpy phase, and I've changed it to internal energy base, and of course I added some libraries for Gauss fluid method itself. And here are some results of the simulation. I validated the solver with multiple shock tube problems. This is an example of shock impact to the water-air interface from air. The shock and the interface are located in the middle of the domain initially. For all of the one-dimensional shock tube problem that I simulated, the method will resolve all of the waves and captures the shock wave quite sharply. And other simulation is in 2D and later a 3D case of the same parameters. So here is a shock wave with 1.9 gigapascal driving to the right with Mach number 1.7 and impacts to an air bubble located in the middle of the domain. Here is a comparison with the low TMP shower that the results are in well agreement with the reference. Here is the simulation. The shock wave first impacts the bubble on the center line, gives a larger acceleration along the center line, which later turns to a liquid jet penetrating the bubble and eventually split it to two parts. And here is a simulation S3D with the same parameters. The horizontal plane shows the shadow graph. We can see the wave interaction, reflection of the shock wave from the interface. And now the jet is penetrating the bubble, and on the left view we can see the effect of the bubble penetration, and the bubble turns to a toroidal shape. So to sum up my presentation, I've developed the compressible GFM solver. To the best of my knowledge, this solver hasn't been developed within OpenFOAM framework before. And there are 3 variants of the GFM in this solver that we've developed, and all of them works perfectly and robustly in capturing strong shock interaction with highly discontinuous interfaces. And here are the references that I referred along the presentation. Thanks for your attention. If there is any question, I would be happy to answer.
Great. Thanks very much, Hassan, for a nice talk.
Thank you.
People have questions, they can ask them in the chat or in the Q&A. While people are typing, I have a few questions. Is the method limited to a structured mesh at the moment, or structured mesh?
Yes, the method is the Venn discretization. Yes, is limited to the structured mesh.
Okay, so that's just related to the implementation of the ghost cell method, or is that?
Yeah, it's kind of for finding the cells surrounding the ghost cells and interpolation. I prefer to transfer the OpenFOAM mesh to a structure format to make the solver much faster. Okay. So that's why I implemented it in structured format, but it is still possible to run it in unstructured mesh. I should make some modifications, but yeah, I will do it in.
And what about parallelization as well? Is it parallelized, or is it difficult to, or was it difficult to parallelize? Yeah. Because I imagine when you're searching across complicated processor boundaries, then it's a real nightmare.
It was a big challenge actually. Both transferring the mesh to a structured format, and that structured format must work in parallel. So I've developed a whole library for handling a structured format and parallelization, and also just you mentioned we need to find some cells from another cells, so we need a couple of layers from another processor, so I needed to find them. I actually find those layers at the beginning of the simulation and keep them for later. So yeah, it was actually
it sounds like maybe that was maybe as much work as implementing the ghost field method is probably implementing that parallelization of that. Very good. I have a question here from Axel. Is ghost fluid method the same efficiency for Newtonian and non-Newtonian interface flows?
Honestly, I don't have any information about non-Newtonian, but I guess it should be efficient. There's no problem with that. But I should mention that for incompressible flows, they actually don't implement the, normally they don't implement those fluidness in the way that they implement it for compressible is totally different. And somehow for making it easier, they just use homogeneous properties as the same as WAF and level set, and they just treat pressure sharply. So it's completely different with what I presented here.
Sure, very good. And then I have a question from Richard Kenny. Do you plan to simulate the shock effects on a distribution of bubbles?
On a distribution of bubbles? No, not really. But the solver can simulate that. There's no problem with that.
Okay, it's just not in your plan.
No,
okay,
it's not. No.
That's fine. Shannon is asking then, I might have missed it. Which Riemann solver did you use?
HLSC.
Okay.
HLSC. Yeah.
Okay. Very good. But and then I have another question. Then maybe you mentioned it, but what are the applications that you're going to use your solver for?
What are the applications?
Yeah.
What do you mean by applications? I mean,
so what engineering problems will you solve with it?
Oh, okay. I have a couple of problems in mind, like simulation of bubble cavitation in a liquid film. I've already simulated that with the compressible WAF solver of the OpenFOAM. So I might simulate that with cost fluid method as well. And yeah, that's the first one that I'm working on, and it's used for printing purposes. So
okay, great. And then one more question. The ghost method is implemented with any, or is the ghost method implemented with any special turbulence model?
No, it was implicit. What I implemented here was implicit, but DBNS foam has another version, which is DBNS turb foam, which considers turbulence.
Okay.
And the solver needs modification. Yeah.
Okay.
To work with that.
Okay. Okay. So you weren't using turbulence here because it's implicit. Fine. And then since we have time, we've only 2 talks. Shannon also has a follow-up question. Did you use muscle reconstruction? I might contact you on the meeting hub as I'm also editing DBMS foam of it. So did you use muscle reconstruction?
No, not really. If it means for the interface, I used Venn algorithm, Venn discretization.
Okay.
I think reconstruction he means for the interface, so I use Venn.
Okay, great. It sounds like Shannon might be in contact. Okay,
yeah.
we'll
I'm really happy.
Perfect. Thanks so much again.
Yeah,
It sounds for a very nice talk. So
thank you.
Feel free to turn off your camera now. And Oliver, I'm ready to hand it over to you. So if you want to turn on your video and you can share your screen when you're ready. Very good. I'll let you introduce yourself.
Okay, thanks, Professor. So my name is Oliver Oxterby. I'm a researcher at NGIS. And I will be talking about generalized internal boundaries applied to high-speed compressible flows. And specifically, I'm going to be talking about compressible flows in solid rocket motors. And this is work that we've done together with our industrial partner, Armscor in South Africa. So in outline, I'll first just be giving a brief introduction to the 2 sort of main pieces of technology which make up this application, generalized internal boundaries and density-based flow solver, and then briefly give 2 examples, a validation case and a application case. So as an introduction to solid rocket motors, they basically are a tube which consists of a solid grain, which is the thing that burns, And the rate at which this burns is partially dependent on the pressure, but mostly what controls the thrust in these rockets is just the surface area that's burning. And so this leads to these very sort of intricate patterns that you see of the shaping of the void in the middle of this solid grain in order to try to end up with a certain specified thrust profile for the rocket. So this is an example of that at the top. It's the so-called Finicil rocket, which has these large fins that give a higher thrust at the beginning to try to accelerate the rocket as quickly as possible to its design conditions, and then thereafter maintain a more steady thrust. So the current way of doing this grain design is quite a sort of cumbersome process. It involves marshalling several different programs to do the CAD, the meshing, the steady state, quasi-steady flow solution, and basically a very labor-intensive process of iterating back and forth between those different components. So the idea was basically to combine all of these into a single simulation. So the first component of this then is something which has featured in previous OpenFOAM workshops, the generalized internal boundaries, or GIBs. So basically the idea is that we can have a finite volume boundary embedded within a volume mesh. And the way that this works is we have some sort of target geometry, and then moving over a background mesh, which doesn't have to be structured as shown here. The background mesh is then snapped to it in much the same way that Snappy Hex Mesh would do it. And that obviously then can often be moved around. The advantage of this compared, for example, to a cut cell method is that you don't have any topology changes in the mesh. It's actually a purely mesh motion problem, but obviously a very discontinuous one at the surface of the geometry. And so that's where a lot of the challenge in this comes in, that where you have these cells which have a large proportional change in size at the surface, the standard sort of mesh motion ALE formulation really amplifies small discretization errors to the level that you get a very, very noisy signal on the interface. And so for that reason, a two-stage process was developed, which basically, first of all, involves a conservative redistribution of the old time field, followed by the standard mesh motion algorithm. And so the particular extreme example of this is when you have a mesh cell actually snapping outside of the geometry, and it's essentially inflating from a zero size. And so there's no sort of time history for that particular cell, and that's where this redistribution has to come in. So at these snapped faces, we then have to basically disable internal faces on the finite volume mesh, and these can then get replaced by a standard boundary condition. One on the inside and one on the outside of the geometry, or one on each side of the geometry. And the advantage of this then is that any standard boundary condition can be used. Unlike, for example, an immersed boundary method, there's no special treatment and you do get an exact representation of the boundary. And so this ultimately allows us to do these kind of complex deformations like you see here, things like butterfly valves and screw pumps and hard valves and that sort of thing, which wouldn't obviously be possible with standard mesh deformation approaches. So then the second component that we're putting together here is a density-based compressible flow solver, again, something which is featured in previous OpenFOAM workshops. So this originated from the HYSA solver, which was written by my former colleague Johan Haynes and myself at CSR Aeronautics. And this has been integrated now into Helix, allowing us to integrate that GIB technology. So as I said, this is a density-based solver, which allows one to represent shock waves much more accurately than in pressure-based solvers. So similar to row central foam, for example, but it's fully implicit, which gives one the advantage of being to a large extent free of the current number restriction. And typically in practice, this gives you solution times that are an order of magnitude or even 2 orders of magnitude faster than you can do with a segregated or explicit solver like sonic foam or row central foam. So basically the process of extending this code to support the GIBs was really fairly simple. There were just a few of the new operators which had to be extended. Basically, the process involves disabling those internal mesh faces, which are replaced by the boundary faces. So as a very simple first test of this, just a verification of the coding, we have this old faithful case of the moving cylinder, this time in a supersonic flow. And we just oscillate that back and forth in the flow field. On the left, we rigidly move the mesh, and on the right, the cylinder moves through the mesh using the GIB, as you can see more clearly in these animations. And this was just a first verification to check that we get almost the same result in the 2 cases. Then on to a slightly more interesting problem. We have this experiment that was done by OMSCOR. It is the so-called burn rate motor, which they manufactured and ran a test bench firing on. So you see here that there's a pressure tap installed in the end of this cylinder. It's a very simple geometry, as I said, so we can simulate this just with a wedge mesh. And the burning grain is just a simple cylinder. The actual burn surface is modeled by quite a simple boundary condition. There's a semi-empirical formula for the speed at which the interface regresses. And then we simply run that with a constant temperature. And this is adequate here because the flame front width is only about 200 micrometers. So there's no need to do any more detailed combustion analysis. So I will just quickly show you what that video looks like. So then we simply created a block mesh to analyze this. And we know the design condition, we expect to have supersonic flow at the outlet. So therefore we simply chop the mesh off at the outlet and provide a 0 gradient boundary condition, because in supersonic flow we can't have any information propagating in the opposite direction of the flow. And when we run that simulation, we get a result which is quite far off the experimental pressure, which is shown in purple. Having a look at the animation for that, what we see plotting the Mach number in the lower pane here is that we don't actually get the choked flow that we expect in the throat of this nozzle. The Mach number remains at about 0.6 to 0.8. So to investigate this further, we just added a plenum to this outlet here. And when we run this simulation with the plenum, immediately we do get the choked supersonic flow in the throat. On this animation, we have plotted in black the Mach 1 contour. At the top, the shading is pressure, and at the bottom, it's temperature. So we have all this interesting behavior here in the plenum, but of course, as soon as the flow has tripped to supersonic in the throat, none of that actually has any effect upstream. So it's rather sort of interesting and surprising that this boundary, or the 0 gradient boundary condition has such an effect on the simulation. just to show then that the actual result from the pressure tap that comes out of this is pretty close to the expected result, except at the end of the simulation, we seem to have some artifacts that are probably due to some geometric imperfections in the actual experiment compared to our model. So although the plenum that we've added to the outlet is irrelevant for the majority of the simulation, it has an important effect in actually establishing the choke flow right at the beginning, which leads to a completely wrong result if we just use the zero gradient boundary condition. But obviously we would like to avoid having to add this mostly unnecessary plenum to every simulation that we do. So we would like to try to model this with a boundary condition that can actually correctly switch from a subsonic to a supersonic condition. And the standard one that one would use for this, Riemann pressure outlet or characteristic-based pressure outlet boundary condition, has a problem of oscillation at this transition to Mach 1. Basically, the pressure is switching abruptly from a fixed value to a zero gradient, and this just leads to oscillations. So fairly much in the spirit of what is done in the awesome flux splitting scheme which we use, we tried introducing this polynomial sort of blending factor. It's the simplest function which blends in a smooth and differentiable way from the fixed value to the zero gradient condition. And that then sorted out the instability. And so running the same simulation then with and without the plenum, but using the pressure outlet, we get virtually the same result. And this is just shown here. We get virtually the same Mach number contours at the outlet. So although this boundary condition is only doing something other than zero gradient for the very first sort of 0.001 seconds of the simulation, it is quite important for getting the initialization correct. Another way to do it is to actually force the flow to be choked right at the beginning by imposing specific initial conditions. But obviously we don't want to be having to impose artificial initial conditions on every case based on a prior knowledge of what the result should be. So then just to end off with a slightly more realistic test case, this is an actual production rocket motor, the B61 rocket motor. So this is now a 3D mesh, which is meshed using helix hex mesh, 1/5 of the cylindrical grain here. And this has that same finisal pattern that I alluded to at the beginning. So this was run both with sonic dim foam and with the coupled compressible solver. And you can see in these animations, we're plotting velocity magnitude at the top, temperature at the bottom, and then this black disk is a slice through the grain, which you'll see eroding away as it burns. So comparing the two animations on the left, you see qualitatively quite a lot of similarity between the sonic dim foam and the helix coupled compressible run. There are some differences which we didn't have time to go to in tremendous detail, but we discovered that there was some significant mass conservation loss in the sonic dim foam case. And this we attribute to the fact that the density-based solver, in contrast, is formulated in terms of the conservative variables, so that prevents any issue of non-conservation of mass. And that seems to have quite a large effect in the case of this pressure vessel type of domain. So we did two analyses with different time step sizes. As you'll see, we were able to use a much larger time step size than for the sonic dim foam run, which contained about 120,000 time steps. with the implicit solver, one isn't, as I said, limited by this current number restriction. So it's possible to choose the time step simply based on the physical features of interest that you want to reproduce. And running this with 1,000 time steps, the runtime then comes down from about 45 hours to 3.5 hours. And making the time step coarser still, the runtime comes down to 2.5 hours. And you can see that the results are broadly the same. Some of the vortices are just not quite as accurately captured. And just in graphical form, some of the results of this, you can see the surface area burning down as the fin parts of the finissel are eroded initially, and then a slower burn away as the rest of the cylinder is eroded. The pressure ramps up to 1 × 10⁶ pascals throughout this. There's some oscillation in the mass flow rate as the throat initially chokes and unchokes. And then the final quantity, which was actually being designed for, is the thrust, which follows a bit more linear profile. So in summary, then, this gives the client a more practical end-to-end way of designing, of doing this grain design process instead of having to marshal these independent separate programs. The addition of the coupled compressible solver did produce significant speed gains. And the new outlet boundary condition allows one to run the simulation without any special type of initialization required. So thank you very much for your attention, and if there are any questions, I'll be very happy to answer them.
Great, thanks very much, Oliver. That was a very nice presentation with nice animations, which are always good to see. I have a couple of questions here. In the Q&A, if anyone else wants to add ones, feel free to type them. So Andre asked, could you also include surface aligned cell layers around the GIB?
At this stage, no, the GIB doesn't support layers, but we do have some plans to add that in future. But no, at this stage, the sort of disadvantages are that you can't have layers around the GIB, and you are also restricted in terms of how fast it can move. Basically, you have a kind of a mesh current number restriction on that. Also something that we're looking to find a way around in the future.
Sure. So I guess the nice thing about the GIB is that you don't have topology changes, because once you have topology changes, then everything becomes much more difficult from a meshing perspective and field mapping perspective and things like that. So yeah, I'm interested to see what you will come up with. That I guess you can't avoid topology changes if you have to include layers, I suppose.
Yes, I won't start getting into that now.
Sure. I guess, yeah, that's the one challenge, I suppose, is like a bit like immersive boundary, that the worst cells are at the interface, unfortunately. So, but very impressive. I have a question from Richard. What factors determine the mesh resolution in the combustion example?
We haven't really explored that too much. The shock in the actual nozzle is not a sharp shock, so there's not really an issue there. So yeah, I think that obviously the larger gradients tend to be in that sort of nozzle outlet region. So that's where most of the mesh refinement happens, but that's really the only factor.
A following question for me is, does it work with adaptive mesh refinement, or is that something you want to do, or?
It certainly could, and we've used the compressible solver with adaptive mesh refinement to actually refine in the shock regions.
Sure.
Maybe there would be a little bit of sort of housekeeping we'd have to do to combine that with the
Sure.
GIB meshing, but it's certainly possible.
Great. Let me see, make sure I'm following the questions in the right order here. Andre came back with another question. Could you have used row pimple foam instead of sonic foam, and I would add on our row central foam as well?
Certainly could have, yes. So row central foam would give a very similar result to what you see here, except that it's an explicit code, whereas we're talking about an implicit code here. So we would have been restricted to very, very small time steps, probably even smaller than with the sonic dim foam case. Yeah. Row simple foam or row pimple foam, I think, from looking at the code, is very, very similar to sonic foam. So
yeah, I think in one, I can't remember which one of the versions of OpenFOAM, maybe people in the chat can say, but I think sonic foam was merged into row pimple foam in one of the versions of OpenFOAM, I think, anyway. So
that wouldn't surprise me. Yeah.
Yeah. Okay.
Essentially the same. Yeah.
Yeah. And Esan asked, is boundary deformation available for GIB? So I guess, Esan, are you referring to kind of like the changing shape of the boundary, the CAD, I guess?
Yes. So obviously as the grain burns back, we do have this deforming boundary, and one can have, boundaries deforming in various different ways. One can have a solid body like a boat floating in water. One can, obviously, one could then couple this across to a elastic solver or something along those lines. The possibilities are really endless.
So then actually, I have a follow-on question. How do you represent the geometry of the interface? Is that like an STL facet geometry, or is it something analytic, or what?
Yeah, so it's just an STL file. I mean, one could do it in various ways, but the methods we have at the moment are just described by specifying an STL file.
So for the deforming, say, interface of the solid fuel, is that multiple STLs, or are you actually deforming one STL?
No, that gets deformed. So basically, one starts with an initial STL, and then it's just deformed as the burning just regresses it back in the normal direction.
Okay, sorry, that follows the. So, okay, sorry, you gave an expression in that case that it follows. Okay,
sure.
Very good. I have one from Anonymous. For the B61 case, increasing the time step by 10 times didn't reduce the simulation time that much. I think you had to increase the pseudo time iterations a lot. Am I right?
That's right, exactly, yes. So with a larger time step, the solver has to do more work at each time step. It essentially becomes a kind of a quasi-steady analysis of those sort of sizes. So you basically at each time step doing a kind of a steady state analysis.
Yeah, and then a follow-on question for me is then for your coupled solver, what is coupled? Is it pressure velocities coupled, or is temperature coupled as well, or temperatures outside of that?
Yes, no, all three are coupled. So it's written in terms of the conservative variables in the manner of traditional density-based solvers.
Okay.
So what you're actually solving for is density, momentum, and energy. And those three are coupled, which is obviously then translates to velocity and pressure and.
Okay. Very good. Yeah, but it's essentially the same block coupled framework as the incompressible engine solver we've seen in other talks. Then it's the same.
That's right. Yes.
Great. And let me see. I don't see any more questions. So thanks very much for a very nice talk. And I'll bring this session to an end. So great, and I'll see people tomorrow then. So thanks again, Oliver and Esan, for very nice talks. And bye to everybody else.